what about the wall? Do you consider that length between C and the wall?
Yeah, so the reason I choose C and not the wall is because no matter how A moves or B moves, this distance is not going to change. This distance will not change because that's fixed. So moving it here won't really make a difference. But yeah, you can absolutely use the wall. Okay, so then once we choose the datum, then the second point is what are the things we're interested in? We are interested in the motion of A, that's given. We are interested in the motion of B. So I'm going to assume that xa is the distance moved by A, or xa is the distance of point A from the origin or the datum. Xb is the position of B, but instead of putting the distance from the wall to B, I'm just going to put it to this point because motion of B and motion of this point is going to be the same. This is just a step which simplifies things for me. Well, as I said, in principle, you could write xb and then you could take L, and then you'll see that the L, which is the length of this particular string, doesn't change. So really, it doesn't help me much. So I'm just going to use xb to be the thing which I've shown over there. Okay, so then, okay, we've set that up. Now we got to use, let's see. Okay, so let's say that this is what I think is good enough, and let's try to proceed. If I need to define more distances, they'll become obvious, and I'll define them. In general, if you see that there are two strings, right? In this case, there's one string wrapped around like this, and another string wrapped around like that. Remember that you will have to define 3 lengths, not 2 lengths. I defined 2 lengths here, but you require a third one.
Why not XD?
XD, yeah, you will have to define that. I was just trying to get to that when I write the equations. You will have to define that. So once you do it, you see that you need to define XD. Yeah, question?
As far as moving away from the data being positive and going towards it and negative, does that only apply to the object moving, or does that apply to the direction the flow is going?
I think the direction doesn't matter. You just have to assume that once you assume the datum to be one side, you always take everything to the right of the datum is positive and left is negative. The thing we're talking about is things moving towards and moving away is using the relative motion, which is another way of solving this problem. Remember, I talked about if one unit moves to the left, then how much is the change in length over another pulley. Last time I just said that's an intuitive way of understanding this. You could do that. That's what you're hinting at. Just that I wouldn't recommend that, because when things get complicated, that logic just can be counterintuitive. It works good for some problems. So in this case, it's as simple as defining distances. Everything to the right is positive. You could also assume a datum to the left, sorry, in this case left, and everything to the right is positive. You could assume a datum this way. You take everything on the left as positive, absolutely fine. As long as you're consistent with what you do with all the distances, you should be fine. Okay, so in this case, I am going to write, the fourth step in the algorithm is to find the length of the string, since the string is inextensible. So length of string wrapped around, I'll call that pulley B, C, D, okay, which generally indicates this length. So that length BCD is constant, and that's given by, I need this length, and I need this length. So that is twice XB plus XD. I think that's about it, right? So if I differentiate that with respect to time, this expression, with respect to time, I'll get 0 equals twice x b dot plus x d dot, which is I'm going to write x d in terms of xb. So x d dot is velocity of d equals minus 2 times velocity of p. The second string which I'm interested, or the cable, is the one which is wrapped around pulley D.
You say that
Oh, so this is twice BE,
okay.
and this is BE, and then when I move this to the left side, I get this. So I skipped a step. VB, VD. Okay, so then the length of string wrapped around pulley D, or let me say pulley D and A. So let me use a different color. So I'm interested in this length. Okay, so what's that length? Let me write the one which I can clearly see over here. This length is simply xa minus xd, right? Okay, I also need to write an expression for this length. How can I do that? So I wrote this one, I need to write this one. What's the overall length? From the datum. Oh, okay, so you're saying from the datum, which is this, to this wall. Yeah. So in this case, you got to introduce another variable. I'll call it d, which is the distance from the two walls, right? And the only reason I do that is because I observe that d is a constant, right? D does not change with time. So one of the steps in the algorithm, I think it's step 3, is to figure out what are the distances which do not change with time, and one of the distances which does not change in time with time is d. Just like the length of the string, the total length of any of the strings does not change with time. So that's d. And so in order to write this length here, it's going to be simply d minus xd, right? No, it's d minus the length from here to xd, right? That's going to be this length. So d minus xd. So let's differentiate with respect to time. So I get 0 equals xa dot minus xt dot. D dot minus xt dot. What is d dot? It's 0 because the length between the wall and the datum does not change with time. This is 0. So if this is VA, this is VD plus, it's going to be plus 0 minus VD, which gives me, I believe, VD equals half VA. So I have an expression for VD from the first expression I derived. I have an expression for VD from the second expression. So from 1 and 2, minus 2 VB is half VA, which means VB is a quarter of VA. And since VA is 3, it's going to be 1/4 of 3, which is minus 0.75. Okay, so as I said, what this is telling me is there are two things it's telling me. One is that the magnitude of the velocity of B is going to be 1/4 of velocity of A. It's also telling me that the direction of motion of B is going to be opposite to the motion of A, as indicated by the negative sign. So you can see obviously when A moves to the right, B is going to move to the left. Okay? That's intuitive from the figure. So as long as your datum is consistent, your XA, XB point in the direction shown, the signs will tell you the direction. Okay, this is clear? Okay, let's do the second problem. And this is where you might need two datums. Let's see.
So what's that? Sorry, what's that thing after the negative 1/4?
VA. This one?
Times 3.
Oh, it's not 3. Oh, we decided.
Yeah. Okay, so next question. So the roller A, which is right here, is moving with a velocity of 4 meters per second. So it's shown over here, it's moving to the left, and has an acceleration of 2 meters per second square. So VA is this, A is 2 meters per second square. So the direction is not given, but I'm going to assume that the direction is going to be left. Okay, move to the left, but could be that A is to the right. There's no reason why it should be the left. So when XA is 3 meters, so when A is at 3 meters from the right side, from the right wall, find the velocity and acceleration of B. So we need to find the velocity of B, acceleration of B, so this is a problem where you could assume, you need to assume two datums because motion is, there's motion up and down for B and there's motion left, right for A. So I'm going to just assume that the first datum, the vertical datum is right here, because I want to relate the motion of B. So I'm going to call this YB, and then since XA is shown to be the left side, I'm just going to assume that this is my other datum. Okay, so the other thing to note is that there's only one single string. So most likely when you solve this, you'll have a single expression for the length which you'll differentiate once to find the velocity, and then you can differentiate again to find the acceleration. So let's try to relate the length of the string passing over the pulley, sorry, not over the pulley, but connecting A to B. So length of the string from A to B, let's call it LAB, equals so I need to find the length of the string, the thing which I drawn in blue, as a function of things I know, XA, YB, and then what else? 4 meters. So this is the easier one. This distance is YB, as you can see. I also need this distance. Okay, how can I find that distance? Pythagoras theorem. So what I know is, I know this distance, it's XA. I know the vertical distance, it's 4 meters. In fact, you'll see that when the roller moves left, right, the distance 4 meters does not change, right? Because this is a finger. So no matter how this moves up and down, this point will not change. It means that this vertical distance will be constant, distance 4. So XA square plus 4 square, this basically gives me this distance. Right, Pythagoras theorem. Okay, so now I just need to differentiate with respect to time. So differentiate, we have the derivative of length AB is 0 because it's an inextensible string. Then I have YB dot plus, okay, the derivative of something under the square root sign is 1 over 2 square root XA square plus, so 4 square is 16, I'm going to write that down. And then I need to take the derivative of the thing inside the square root, which is XA square plus 16. So it's going to be 2 times XA times XA dot. So if you think this is hard, you got to go and revise the part on taking derivatives.
That's chain rule?
Chain rule. So, yeah, question?
You made it simpler by just like plugging in 4 to 3, or actually 3.
No, you do not want to do that right now, because if you plug in 3, then when you take the derivative, you'll get YB dot equals 0. Right? So let's say, that's not true. When that thing, when A moves with the velocity, B also moves with the required value. Yeah, the reason why I put in 4 here is because it's constant. When something changes with time, you do not plug it in. You only plug it into a tray.
So then you find point B at that instant, right?
Yeah. Eventually, yeah. So now I can put in the value for XA to find XA dot. Sorry. I plug in the value of XA to find YB dot. I know what XA dot is. It's 3 meters per second. So this is VA. This is VB. So VB equals minus XA VA divided by square root XA square plus 16. So this will give me minus 2.4 meters per second, where I've put XA equals 3 and XA is 3, right? Yeah, XA is 3 and VA is 4. So after shoving these things inside this equation, I get minus 2.4 meters per second. So what this is saying is that when VA moves to the left, VB is negative. That makes sense? When VA is moving to the left, VB, velocity of B, is negative. The positive direction is downward. It's saying is that the negative direction is upward. It's saying the velocity of B is going to be negative, or it's going to move upward. It makes sense. Like move to the left, B moves up.
So the question like this, sign is not a big deal. You just assume that
the sign will show up in the answer. So
when you choose it the other way around.
Yeah, if you choose the other way around, then what will happen is I would have to take, let's say that I choose this to be the origin. I would recommend it, but if you choose this origin and you choose y be positive, then this will become negative in that expression, because then if you do not do that, then that length is not right. You want to find the, since you go this way, if you assume that y be positive in this way, then this length is negative because it's downwards, and your origin is right here. Yeah.
Another way of to think about the signs would be that the distance is being reduced or extended in a table.
Yeah. So that's what I would recommend not doing, which is the way we've done this problem is we've assumed absolute distances, and the other way to solve this is to assume what happens when A moves slightly to the right, how much does this drop down, and you can use that later on to understand, but I wouldn't recommend using that to solve the problem. But that's another valid way of solving. That is, what you do is you say, okay, if A moves the distance of XA units to the right, then how much would this change? That leads to all sorts of confusion, because then you have to see how that tangent changes, and it's too complicated. Just do it this way. Okay, so once you have VB, you want to find AB, right? Because you also told to find the acceleration of V. So this is as simple as taking the derivative of this expression. So A, B is VB dot. So it's going to be the derivative of this thing. So you're going to take the derivative of okay, so again you got to use commutative rule, which says that you got to first take the derivative of, I'm going to move this negative outside. Okay, so first to take the derivative of xa, so that's going to be xa dot, keep everything else as it is, then you keep xa and the square root as it is, take the derivative of whatever is left, which is va, so it's va dot, and then finally keep xa and va constant, and then take the derivative of whatever is left, which is the square root sign. So it's going to be xa square plus so when you have minus half, it comes to be 3 divided by 2. What's that?
Can you use quotient rule for derivative for this one?
Cost rule.
Quotient.
Quotient rule. Yeah, that's, what's the quotient rule?
One that you split the bottom.
Yeah. That's exactly what you need to do. I do a mistake here. So if you want to find the derivative of 1 divided by f of t, anybody remembers how to take the derivative of 1 over f of t? It's square, f of t square, right, times so f dot t, negative f dot, is that right?
Yeah.
Okay, so I got to use this. So I got to use this thing on the last expression here.
That's what I meant by.
Yeah. Exactly. So x plus 16 square, and then you got to take the derivative of whatever is inside. So 2xa So what you know is XA is 3, VA is 4, XA, well, this is also equal to XA dot, right? Velocity is XA dot. And then you also have to find velocity of A dot, which is acceleration, which is given to be 2 meters per second square. So that's 2. So after putting all that in, AB equals minus 3.25. So check this value. I'm not too sure about this value actually. But the negative sign is obvious. It tells me that when A moves, accelerates to the left, B is going to decelerate upwards, or acceleration of B is going to be upwards. Okay, any questions on this? Yeah, so please solve more problems. This is very important, and it's very easy to get lost in this by assuming relative distances. Just blindly assume follow the algorithm, and you should get it right. Okay, I'm going to spend the rest of the class on 12.10, which is on relative velocity. By the way, we've not been able to finish grading on your exam, but I'm pretty sure we'll get it done by today. So next class, before next class, you'll have your grades. Okay, so what we did in 12.9 was absolute motion. All the distances XA, XB, which I showed you, were about the origin. They were moving relative to an origin which was fixed. Now we're looking at motion which is relative, which is saying that if two people are moving, then you want to find how the motion of one person changes as with respect to the other person. And of course, both people are moving. So that's what is known as relative velocity. So a little bit of conceptual overview before we get to problem solving. Okay, when I say ground frame, it means that this frame is fixed to the ground, it doesn't move, or fixed to the earth, it doesn't move. We also have another frame or axis which is moving. In this case, we are only interested in translating axis. It could also rotate. I'll call that x prime, y prime, z prime, and it is a translating server. Okay, and if there's a particle, let's call it B. Let's call the origin of the translating observer to be A. Right? Then I can find the position of A with respect to my fixed frame or ground frame. I could also find the position of B. This is a particle which is moving. So the position of B, and relative velocity is when you're trying to find the position of B with respect to A. Okay, so B is a particle which is moving, A is an axis which is also moving, so A and B both are moving, and what we're interested in this particular part of the course section is that we are interested in this particular vector. It's called the vector B with respect to A. Okay, so an example would be let's say that when we say launch a spaceship in space, okay, so the astronaut moves in the plane, and we are trying to keep a track of the astronaut with respect to the Earth, right? So then what we can do is we can keep a track of the space shuttle. That would be A. The astronaut is B. And to find the position of the astronaut B, what we need to do is we need to find the position of A with respect to ground plane, to find how B moves with respect to A, and that can be used to find how the astronaut moves with respect to Earth. So it's just an easy way of keeping track. Instead of trying to keep track of all particles with respect to ground, you keep them, you find how B changes with A. So it's much easier to then find how it moves with respect to ground. So if I have drawn a closed triangle with vectors, then I can relate B, A, and B with respect to A. RB is RA plus RB with respect to A. I hope you can recall this from vector algebra, right? If you have a triangle, closed triangle, then the vector from 0 to A pointing that way, 0 to B, sorry, is pointing that way, is the sum of the two sides, right? Provided the arrows are as shown. I forgot to draw this arrow. I should draw this properly. This should be an arrow this way. So all you need to do in order to find the relative velocity is take the derivative. And then if you want to go a step further and find the acceleration, it's just the second derivative of position. So relative velocity is VB with respect to A. It is simply VB minus VA. How did I get that? Well, I just used this formula to get, I just move A on the other side, and then the relative acceleration is A, B with respect to A is and I got this from the acceleration formula. Okay. So this will become clear when we do problems